we need to cover is the key management. Basically, we saw three cryptographic mechanisms, which are symmetric key cryptography, asymmetric key cryptography, and hash. Basically, these are the three kind of cryptographic transformations we saw. And for the two first symmetric key and asymmetric key cryptography, we need keys, and the keys should be managed. So basically, they should be generated, they should be shared, they should be distributed. Okay, and so all this lecture is about those issues. Okay, so we start by the symmetric key cryptography. So basically, in symmetric key cryptography, the keys are secret. Okay, between the sender and the receiver, and they need to be shared somehow. So symmetric key cryptography is more efficient than asymmetric. Yeah, we saw this symmetric key is more efficient, but we need to share the this secret key. So we need to share the secret key between the two parties. So the distribution of the key is a problem. Okay. So the most typical technique for sharing secret keys is to use a key distribution center. So basically, two entities, most of the time, they don't just exchange the secret key directly. They need to go through a key distribution center, and of course this is a trusted center. So each user will share a secret key with with that key distribution center. Now
the public key.
Here
it's only one key.
Depends. It depends. You can do it with public or secret key. And basically, the key shared with the key distribution center, it's shared a first time, and it might be quite special. It will not basically to start up the system. When you need to share a secret key with, for example, the center, it might be physically. It might be physical distribution, right? By phone or postal, any physical post, etc. Okay. So you assume here that the distribution center shares a key, secret key, or secret key here. The system here is a secret key with every user. Okay. Now, the key segregates a secret key for each member. This secret key can be used only between the member and the key. So it's a symmetric key. It's not asymmetric. Not between two members. A session symmetric key between two parties is used only once. This is the second sentence will explain it earlier. So this is one model. So assuming that every user has a shared key with the distribution center, this is a model how Alice can share a secret key with Bob. Okay. So basically, this is what happens. Alice wants to communicate with Bob with symmetric key. So it will ask the distribution center, I need a secret key with Bob. Okay. So again, the distribution center is trusted by everyone. Okay. So the distribution center will generate the key. So here the distribution center is in charge of generating that secret key, and then it will send the key to Alice. Okay. And here what it sends exactly? It will send the key. This is the key. Basically, this is a secret key between Alice and Bob. Okay. But normally you would say it will just send the secret key. It doesn't just send the secret key. It will send the secret key and something else, which is the identity of Alice, the identity of Bob, whatever it might be, the name or the IP or whatever. Okay, plus the same key, this one, the same one, but encrypted with what here? With the key or the symmetric key shared between, see here, key B, encrypted with Bob key DC secret key. The secret key shared between Bob and the key DC. Why does that?
So that Bob can use the same key with Alice?
No.
Will show authentication.
Yes. Because here, when Alice would, at the end of the day, Alice it will get that key, it knows the key, so it can use it, okay? But it needs to send the same information to Bob, right? Now how it will send it to Bob? How it will send it to Bob? If it sends it clear, it's a problem. If it encrypts it doesn't have anything to encrypt with, because Alice and Rob do not yet have a shared secret key, okay? So it cannot encrypt. So what it does here, it will take that same data which the KDC has encrypted with the secret key between KDC and Bob, and will take it as is and will send it to Bob. Okay. So here, Bob, will it be able to decrypt this message?
Yes, because it has the key.
Yeah, it will, because KB again is the secret key between Bob and KDC. So only Bob and KDC know that key. Okay. Does Alice can decrypt that key?
No.
It can't, because KB is secret between the Bob and KDC. Okay. So this is very simple key distribution protocol. Okay. That allows Alice and Bob to agree on a secret key. Of course, it's not really secret because the distribution center also knows about that. Okay, so yeah, so once they share that key, they can start communicating. Now, do you see here a problem? Can you think of an attack on this system? What is that? Man in the middle.
Between Alice and KDB.
Yeah,
Between Alice and the center.
Alice and center.
I mean, we got someone can actually take place in.
So man in the middle here.
It's encrypted.
It will do what? How?
Before even they distribute the.
No. Here you assume that this one is trusted, and the keys, basically KA and KB, are found. Yes.
Alice know the original message, and he have the encrypted message with the KB. He might figure out the key.
So this is basically, in cryptanalysis, this is the case where the attacker has one plain text message and its corresponding encrypted message, right?
Yes.
This is one scenario of cryptanalysis, but you need to crack it. It will be a little bit easier than if you don't have anything, but still you need to crack it. Okay. So again here, man in the middle will not work. Yeah.
Someone could take place impersonate the KDC.
The KDC is assumed to be authenticated and trusted. Yes. Okay. But assuming it is authenticated and trusted, what might happen here?
Someone can take it too.
Take two?
Yeah.
What do you mean? Here?
Yeah, man in the middle. You see
okay, it can take it, but it cannot decrypt it because the attacker needs to have KA. And KA is only known by Alice and KDC. That's it. Okay. Now here, this is a major problem. Whenever you have such protocols, such a key distribution protocol, you need to check one thing, which is the possibility of replaying a message. Now, okay, Alice here will receive that message, okay, and then it can decrypt it, it can get the key, etc. Now, suppose someone else gets that key, gets that all this block. It can, right? Because it's encrypted, but somebody can intercept it. Okay. Now it can't decrypt it, but for this message, it can store it. It can store it, record it, store it, and then after 2 days, it will replay it. So here, even Alice, Alice can carry out this attack. Basically, it will keep that message for a long period of time, and then will replay it. It doesn't need to know KB here. It knows that key, right? So if it replays it after, let's say, 2 days, it will know that this secret key is that same one. Because here, this message does not have any freshness, any time information. That message can be stored and replayed like a year later. Okay. Now, Alice can carry out this attack. Basically, it can use the same key after 1 year, for example. Okay.
But Bob has to send something to Alice. Bob knows that he is sending to Alice when he uses this key.
Okay. Assume that.
Because the
Okay.
key is only between Alice and Bob, right?
Yeah. This
The key.
this key is shared between Alice and Bob. But let's think about the cryptanalysis. Basically, the case where you have basically I don't know. You receive this. Suppose an attacker went here. Okay, received that message. Okay, so it has all the time to crack that message. So, for example, it has 1 year to crack. It can crack. In 1 year, it can crack. Okay, if it cracks it, basically, it will know what is this key, right? But here, it doesn't need to crack KB because the message is encrypted and it can be used after a long period of time, right? So basically, if an attacker can get that key and it wants to convince Bob that now we're going to use that key, it doesn't need to encrypt it with the KB because it has it already there. It has this message already encrypted, so it will store it. After 1 year, after it could crack this big message, okay, it will just replay that message, replay that one. Basically, it will send it again to Bob after 1 year, and it will open a similar session with the same key. The problem here, okay, you can think about different scenarios, but the problem is that this message is not related to time. Basically, it doesn't contain freshness information. The problem with this, you can store it and you can replay it sometime later. Okay, after 1 day, after 2 days, after 1 year. This is the problem of this. It doesn't have freshness information. Okay, I just described the 2 scenarios, but you can think there are a lot of scenarios, a lot of attack scenarios that can be possible if the message can be replayed.
Now, you said that symmetric keys are usually have they have to be changed every once in a while.
Yes. Yeah, this is the point. Yeah, this is the point. Okay, you establish this shared key now. Okay, you use it for 5 minutes. Okay, then after 5 minutes, you basically change the key.
Yeah.
Then you keep changing it after 5 minutes. After 1 week, suppose the attacker wants to use that same key. Okay, it will just send the message, the same packet to.
But KB now is different from. I don't have this KB because I deleted it.
No, I mean in this.
Bob doesn't know.
This key sharing, each time you change the key, it is redone. Okay.
The same key, the same information.
Not the same key. This process, this protocol. Whenever you need to change the key, you need to go through all this. So after 1 week. It doesn't hurt if you used 1 key now and then after 1 week you reuse that same key. I don't think there is a mechanism to check if the key.
Why can't we just add the time?
Yeah, this is basically to fix this. You need here in this message. Basically, the next protocol we will deal with it. You need to add some freshness information. So either time or some random number, or sometimes you need to ask Bob for a challenge. Okay. So basically, an attacker who just recorded that message, he cannot solve the challenge. I'll show you how this is done.
So,
Yes.
how does Bob know KB?
It's his key.
It's his key, yeah. KB encrypted with Bob KDC secret key. So KB is the Bob KDC secret key. We assume that basically in the previous slide. We said, KDC shares a secret key with every user. This is the assumption. Okay.
So why doesn't Bob take his key directly? Why does Alice send it to Bob?
You mean by the takes his key directly? So basically, the KDC will communicate with Bob directly.
Yes.
Yes.
Why is Alice sending the KB?
Because it is the one that initiated the communication. In practice, it is not very practical to do that. Ask KDC to send the key. Basically, Alice is for example, is the client. Just to establish a connection with Bob, so it needs to do all the job of session initialization. Now this is Schroeder. It's much better protocol where we use the same assumption. KDC and Alice and Bob. Alice wants to share a secret key with Bob, and here see it contains more steps, and all this is to deal with that replay attack. Okay. So basically here what happens. Alice sends the definition, the identity, of Alice and Bob, plus some RA, which is a random number. So basically, this will be a challenge. Random number that will change all the time. Okay, every session it will change. Okay, so KDC will answer with what? With Alice. This is the key for Bob, right? This is the key for Bob, and then this is the key for Alice, and the definition, the identity of Bob, and the same challenge replayed. The same challenge encrypted. The same challenge encrypted. Okay. So here, nobody else can claim to be KDC because you need to get that random and you need to be able to encrypt it. Okay. Fine. Then Alice will send the ticket which contains the key, just the key. Now, up to now, the same attack can be carried out, right? Because somebody can intercept that message and then keep it for a while and then replay it sometime later. Now, to avoid this, there are two steps. Basically, here, Bob will show that he could decrypt that message, and it will basically generate some random number encrypted with the new shared key. The new one, KAB. Now KAB is this one. Yeah, this one. The session key. Encrypted with Alice Bob session key. Session key between Alice is the same here. KAB and this one is the same. Okay. So basically, it will encrypt that random number, and that random number again is generated by Bob. Now, Alice, to prove that it is really Alice, and she has really that shared key, it will take that same random number and subtracts 1 from that value, encrypt it again with the same key and return it back. Why we subtract -1 here?
Because it's
the same. Because otherwise it's the same data. It can replay the same message. Here we just do -1, change slightly that random value, and then encrypt it and send it back. Okay.
And this random value is the freshness information.
Yes, it is the freshness information. It's random. It's generated every session. Yes.
Can the attacker contact the KDC and get session key and or it has to have
So basically, an attacker will contact the KDC.
Yes.
To get, he can. Every attacker is normally is a user in the system. It can contact the distribution center, but it needs to specify what it wants and which key it needs to the DC to generate. You cannot ask the distribution center, please give me the shared key between X and Y. It doesn't work like that.
Then what is Alias sending? ID or?
No, here Alice, what it needs to do, it needs to generate a shared key with Bob. This is why it connects to. Now, if another attacker wants a secret key with Bob, it will provide its own identity and Bob.
But this connection is not encrypted. I can.
It is not. It is not. It is not.
So can the attacker take it and replay it?
Replace with what?
Replay it.
Replay it. It can.
And get.
But then, if it replayed, the next step needs to have KA to keep going. Okay, so this of course this message can be replayed by anybody because it's in plane. But so what? Then the next step you will be stuck if you don't have the KA. Okay.
I didn't understand how this provides freshness.
Here. Okay. Okay. Now this freshness, you have two freshness values, RA and RB. The second one or the first one, or both? You want both? You don't understand both?
I don't understand where is the freshness coming from.
The freshness is that if somebody keeps, okay, suppose an attacker wants to replay this message. Wants to replay, he will record that message and after 1 week it will replay. Now, suppose it recorded, now it contains RA, some value, which is related to the current session. Now, later, after 1 week, if the same thing, Alice wants to communicate with the bot, it will supply another value of RA. Okay, so that same message recorded 1 week earlier will not work. Okay, so this is here. The same thing here. Here, if an attacker basically wants to replay that message. Replay that message. Okay, so basically it will send that same message after 1 week to Bob. Okay. Now, Bob will make sure that I am talking to the right person. It's not someone who is just replaying that message. It's really Alice. So it will challenge Alice with that random number, with just freshness information. So basically, Bob will challenge Alice. Are you sending the message right now? Okay. So basically, it will contain a random number, and Alice here needs to extract that RB and subtract one and encrypt it again. Okay.
We assumed previously that an attacker took the previous message and he could get the shared key KAB.
This is one scenario. This is one scenario. Yeah. This is one scenario of that can happen with the replay attack, but it's not the only one. Okay. This is a valid scenario because the attacker will basically try to crack this packet. It will take like 1 week to crack it. He will crack it finally. He will know the he will know the KAB, this one. Okay. And now what he needs to establish a new connection like 1 week later with that same KAB, with that same key.
Yes. So he will replay.
He will replay this one.
Yes.
But if the communication stops here as in the previous protocol, it might work. It will work. Okay. But here there is another challenge. He needs to respond to these two challenges. Or
He has the KAB, right?
Then we assume actually others is
Because it's the key. It's the key in key A. You have RI Bob and the key which is KAB.
So here we're assuming the scenario that the attacker could
No, it's KAB.
so knows the KAB.
Yes. So RB you can get RB.
Yes. So basically, if it knows KAB here, it could.
Yes.
Yes.
KAB actually is the black key.
Huh?
KAB is the black key.
Yeah.
And the black
So if it decrypts this, it could respond to all challenges here. Right. In this scenario, it's a strong scenario here. So you're assuming that the attacker could crack this packet. Basically, it can respond to all the next challenges because now.
It can't replay KB. It can't replay KB.
This one?
Yeah, this one.
It can. Because it's stored, it's recorded.
But what's the point? Because this packet has Alice address. The attacker wants his address.
No, here it's right in the middle. It will stand in the middle, so it will see all the traffic going on.
But after 1 year, the attacker wants to replay it with he's not in the middle anymore.
Here, assuming someone is watching the traffic, it's not a difficult
All the
assumption.
time, keep it under.
He's watching all the time. Okay. Yeah, you are right. Here, if in this again, so what I want to tell you, the possibility to carry out a replay attack can be used in a lot of scenarios. Okay. I explained to you one scenario, and that scenario is very strong. Basically, if the attacker could decrypt this, this will not help. Okay, this will not help. But replay attack can be used in so many other scenarios. Maybe in the others it's not as. This challenge will stop.
Now,
Yes.
is the encryption has a specific format, or is it just?
Symmetric key.
Yeah, it's symmetric. I mean, you are giving the identity and the key.
Yes.
The key, yes.
Yes.
So is it always like that formatted, like the address then the key, or it's randomized?
Why?
Well, because I can actually change the keys. For example, I can be in the middle, intercept the Alice signal.
And then you just change the part about the
Keys, yes.
No.
You have to look for it.
No. No, you remember DES and AES they have that avalanche effect. Remember that avalanche?
Yeah.
Avalanche change one bit, everything changes. So you cannot just say, okay, the first 10 bits is about the key and the last, it's mixed up. Okay. Yeah. So yeah, here it's better than the previous scenario because we have some challenges and some kind of random values, but still it's not 100.
Isn't the key should be updated every 5 minutes?
Yes.
So it's very hard to keep and crack the.
But yeah, again, you can of course it will stay for 5 minutes. But the problem is after 1 year, for example, you need to, or the attacker will try to establish the same session key, the same one. Okay.
Yes, you're right.
And you will be using it for 5 minutes. So basically we saw the simple one, this one, this one, simple key distribution protocol, then Needham-Schroeder protocol, and then there is this is basically in practice what is being used in Windows 2000, for example, to guarantee key distribution and also authentication. So Kerberos, the name of the protocol is Kerberos. Is an authentication protocol and at the same time key distribution center. Okay. That has become very popular. Several systems, including Windows 2000, use Kerberos. So this is how it works. Basically, the key distribution center has two parts. It has the authentication server and the ticket granting server. So here, where we need this protocol, this is server. Okay. So the client here. Or user wants to access some server, okay, some secure server. You need to have a privilege to access to that server. So that server may be, for example, FTP server. Okay, there is, and you can think of it as a local area network or intranet where you have available services. So FTP, I don't know, mail, whatever. Okay, and the user wants to use that service. Okay. So it needs to go through two steps, basically the authentication and then the ticket granting service to get the key. So how it is done? The user will request the ticket for the ticket granting server, and of course here this authentication system basically Alice needs to provide some credentials like passwords, for example, some user password, etc. The authentication system will check the identity of Alice. So the identities are checked here, okay, in the authentication server. Then that authentication server will generate an Alice TGS session key and ticket for the TGS. So basically, Alice Bob session key and ticket for Bob. Yeah, the same thing. Basically, Alice will contact the ticket granting server to get some secret key with Bob, basically the server. Okay, and again here what the ticket granting service will provide, very similar to Needham-Schroeder and the previous one. It will provide Alice Bob session key, share key, and then ticket for Bob. So something to send to Bob. Very similar and then that ticket to Bob will be so request access here. In the request access, you will send that ticket to Bob. So this is just enough, but the details. So authentication server, the ticket granting server. The ticket granting server issues a ticket for the real server. The real server provides services for the. here, why basically you say, okay, we need two things here. We need the authentication server and the TGS. Why we will not make it in one single type of communication? Now, why we do this? The authentication is done only once. It is done once, and then each time the alias needs to communicate with Bob to get a new key or to do something else, etc. It does not need to re-authenticate itself second time. Okay, like session generation. When we generate the session cookies, the cookie. Okay, cookies are they generated in all the time? When you need to access some, I don't know, Gmail or mail service or some secure service, okay? You supply your password, you authenticate, so you authenticate only once. Then, do you need to authenticate whenever you need to send another packet? Basically, you have one cookie value, that will maintain your session, right? Okay? So the same thing here. The authentication, supplying your password is done only once, and then the tickets, whenever you want to renew the key or access another service, you will be authenticated to in the authentication server, and you can use plenty of services. Now this is the complete one. So basically, I think it's very quite similar to Nidam Schroeder. Okay, so see here identity. This is identity with Alice. Basically, here when we say like this, it needs to authenticate to that server. So the server will check the identity of Alice. Then it will reply by very similar to the previous protocol. So basically here we have this is a ticket for the TGS, okay, and this is the key or the secret key with the TGS. So it's an additional step. You need to get the key with the TGS, and then later on you will get the key with Bob. Okay. So this will send now if you have that key. Or you have the enough credentials to ask something from the TGS, you will send your request, Alice will send its request, and the TGS will respond with a ticket now, a ticket for Bob, ticket for Bob, which is encrypted with the TGS B, Bob. Okay. Similar to the previous one. So basically this is the thing you need to send to Bob. And then the last step, Alice will send that ticket to Bob in addition to some challenge T or some timestamp. You said timestamp there? Yeah, timestamp. No, so you can think of it as a random number with freshness. Okay, and then Bob, to prove that he's really Bob, he needs to decrypt that ticket with its own, with its shared secret key with TGS, which is supposed to know. Okay. Then it will extract the AB and it will use it to encrypt the same timestamp minus one. So basically, this is the challenge. It needs to respond to this challenge. Okay. Yeah. So basically, the protocol is based on a set of authentication and some challenges. Basically, the challenge to respond to those challenges, you need to know the keys. Clear? I am not here expecting that you understand every single detail of it, because there are plenty of details to understand why we do each one. You need to think of it and take your time to think why we do each one of the steps. But Kerberos is a very common type of authentication in key distribution used in Windows. Yes.
The first packet between the user and the AS. When did they agree on the key?
Which key?
KAAS.
No, KAAS is supposed to be there.
Before the
yes.
Okay.
Yes. Okay. Yes.
Step 3, Alice sent the challenge, but it was not the T of T, the first part. Is this a challenge or? I understand.
Yeah, no, I think it's a T. Okay. So it's timestamp, it is encrypted with the secret key between A and TGS. So normally, only TGS can decrypt that message, right? Now, when it answers here, it responds, this is a ticket for Bob, right? Yeah, you are right. Here,
Maybe there's a missing.
no, it might be the goal is to do it here. The goal is to check the freshness of all this message. Because if it is timestamped, it should be fresh. Okay, some current value. Okay, some current value. Now the check of TGS will decrypt that and will take that value and it will know this is a fresh value because it's related to the current time. Okay, so it doesn't need to answer with some other challenge by itself. This will guarantee the freshness of this message. Huh? Somehow clear. Now the key points here. Basically, whenever you need to establish a session with some other entity like Bob here, you need to go through a key distribution center. The key distribution center, it will do plenty of things, but it will basically generate a kind of ticket to be sent to that destination, Bob. Okay. And it should be encrypted with that destination secret key. Okay. Now, here the use of these value t and t-1, etc. This is for freshness to avoid replay attack, roughly. Okay. Yes.
Doesn't Bob have to connect to authentication center? Because to get TGSB.
Assumed to be already shared.
But we didn't assume that. Well,
We assume.
no, we got AS. We have AS. Here it immediately connects.
So basically, wait a minute here. KAS TGS. So here you are saying that this ATGS it has been generated here, but TGSB basically we assume that
Bob has it.
Yeah, here it's not. Think about it. It's not similar to the previous scenario because in the previous scenario we have Alice and Bob, two entities. Okay? Here we are having client and server. So Bob is a special type of user. It's not just a client. It's a server and it's part of the system, right? It's part of the system. So we might assume that there is some kind of checking or relationship between these two because these are part of the system. This one is the user. This needs to be secured. Okay, but server and TGS, and we might assume that this TGSB is checked somehow. Okay. Doing this session key between themselves without using KDC. This method of session key creation. Yeah. Now. Let's we'll go through the next one and then we'll start. Suppose you have Alice and Bob and there is no key distribution center. Alice and Bob needs to share a key between them without going through key distribution center. Because here key distribution center is another requirement. You need to have some trusted center in the network. Suppose you don't have that. Okay. So how Alice and Bob will share a secret key? So here there is very interesting protocol called the Diffie-Hellman, very known, very used in SSL and TLS is very common. So this is a protocol to basically exchange a secret key in plain text. So all the messages are in plain text. At the end of the day, Alice and Bob will have a secret key known only by they two, okay? And even if you have some attacker watching the traffic, he will not get that secret key. So it's kind of nice mathematical properties to guarantee that. Okay. So how it works? We generate two large values, P and G, which are public. Okay. Here values by values mean big number, large integer numbers. Okay. We agree on them, and they might just exchange them, or one generated and sent to the other. Now the attacker might know these values. Okay, and it's part of the protocol. Now R1, what it does, it will pick one random number called X. It will pick it. This is secret. X is secret. Okay, it will choose one random number X, and it will compute G to the power X modulo P. And this is R1. Okay. Now again, X is secret. It will not send it. It will send just the result R1 to Bob. Okay. Now Bob, what it will do? It will do the same thing. It will generate another number, large number Y, also secret. It should not send it to anybody. It will compute G to the power Y modulo P, and it will generate R2. And it will send R2 to X. Now, both of them will do the same thing. Alice will take that value it received from Bob, and it will put it to the power X modulo P. It will obtain the key. Bob will do the same thing. It will take that same value it received with R1 from Alice, which is R1, to the power Y, its own Y, which is secret, and modulo P. And at the end of the day, both of them will obtain G to the power X to the power Y, G to the power X times Y, modulo P, and this is the secret key. Basically, they can compute the same value, but in different ways. And somebody in the middle here, even if he sees R1 and R2, since it does not know the value of X and Y, it cannot know the K.
Even Bob nor Alice knows X and Y. I mean, like.
Yeah, of course. Alice does not know Y, and Bob does not know X. Okay. Now, this is a way to exchange the keys. So the mischain key is Diffie-Hellman, middle is K, G to the power 2. So this is an example. So let us take an example. An example uses small numbers, but not very large. So if G is 7, P is 23. Now Alice will choose X is equal to 3. R1 will be 21. Bob will pick Y is equal to 6, which are the two secrets, and then R2 will be 4. If it sends, Alice sends 21 to Bob, Bob sends 4 to Alice, and if we do the computation, basically, we'll obtain the same value from Alice and from Bob. Okay. Yeah. Okay. Now, this is an example of the values of Diffie-Hellman. We told you these very large numbers. So, see P here. It's a huge number. X and Y might be not that large, but here is just an example. But again, even with this, guessing the X and Y is quite difficult.
How can we compute this number?
There are algorithms. There are algorithms for modulo combinations.
Also, it has to be prime numbers.
No, here just numbers. This is RSA prime. Here it shouldn't. Just large numbers. Okay. Yeah. So let's stop here.